Hello, everyone. So welcome back to another wonderful PChem lecture. So far, what we've been focusing on lately is how we can use things like valence bond theory, has the other common name of valence shell electron pair repulsion, or VESPR, and MO theory to try and build up some crude estimates of what my molecular orbitals are going to look like, both in terms of shapes and in terms of energies. But it's worth noting that so far what we've done is build up a rough general picture. What we really need now is a systematic way to try and improve these values. So thus, we're going to end up falling back on one of the major ideas of theoretical quantum mechanics these days, and it's called variational principle. So the variational principle is often expressed as the form that what we're going to do is what the variational principle states is that if I have an arbitrary wave function that I'm going to use, so some guess wave function like my valence bond theory, its value as calculated by the Schrodinger equation can never be less than the true energy of the system. So if I have a real system and it has a real energy, that anything I guess can never have an electronic energy less than that real value. So this sounds a little bit like a mouthful, like most technical phrases. But principally what it means is that if I guess take a wave function and I guess a lower energy structure, so I have a function, I guess a new function, and that second function has a lower energy, that second function is likely going to be much closer to both the true energy and the true wave function. This is a really big idea when I'm trying to figure out what my system really looks like. That I can essentially make it work by keeping guessing until I get the energy to a minimum value. And this is going to underlie a lot of what we're going to be doing for the rest of the chapter. And in practice, what this often means is that, let's say I generate a wave function or a structure using a linear combination of atomic orbitals or VESPR or any other method. It's going to give me an original trial wave function. And then what I can do is use the variational principle to sequentially improve this wave function. So every time that I guess a new one, well, energy goes down. That's my new guess wave function. I'll keep doing this till I can't get a lower energy. This is actually what drives a lot of the theory that we've been using in lab. And so, as you can imagine, the variational principle becomes quite important in trying to, in the practicality of trying to describe what systems really look like. So we're going to be focusing a lot on trying to both derive and prove the variational principle today. So really what we can do is we can show that the lowest energy that if I have a trial wave function, sigma trial, the lowest energy that I can possibly get by applying the Schrodinger equation to this guess wave function is going to be the true energy of the system. So where we can essentially start is by starting with this trial wave function and applying the Hamiltonian to it. So because this trial wave function might not be an eigenfunction of the Hamiltonian, we're going to essentially generate it in the form of an expectation value. So the energy of my trial wave function is going to be the expectation value of the Hamiltonian over all space. Nothing too tricky. You might just need to go back from before break till from when we did this a lot more frequently, probably going back to that first test. But by applying this basic quantum mechanical idea, I can start to build up the variational principle. And essentially what I'm going to be doing is by looking at the difference in energies. So how different is this, the energy of this wave function going to be from the true energy? So I can do this by subtracting the true energy from both sides. So when I do this, the left side becomes literally the difference in between the energy of my wave function and the true energy of the system. Nothing too surprising here. But if I subtract the true energy on the left, I have to do the same thing on the right. Now, because I want to make it look kind of the same form, I'm going to multiply my true energy by 1. And I do this by using the normalized trial wave function, because if I'm going to be building up an MO, I want it to be normalized. So if I take the probability of this trial wave function existing anywhere in space, this gives me a value of 1. So this is, again, the same thing as subtracting the true energy from both sides, just a little bit more cumbersome. So using this basic form, I'm going to be looking at the difference in energies on the left. Most of what I'm going to be doing is trying to simplify this right side. Now, first easiest way I can do to simplify the right side is making these two terms look a little bit more like each other. And I can do that by bringing my true energy inside the wave function and treat it like an operator. So can pull the true energy of the wave function straight into the middle term. I can do this because my true energy is just a constant, and my constants can come in and out of that integral as much as I want. Now, one of the reasons why this actually is fairly useful is because I turn that true energy from being a value to an operator. And then I can make use of some of the principles we used at the beginning of the semester, and saying I have a combination of two expectation values, and that's going to be the same thing as doing the combination of the two operators. So I can turn this longer expression to a much more simple expectation value of the difference of my Hamiltonian minus the true energy. All right, should hopefully make sense, because the goal of, if I'm applying the Hamiltonian minus the true energy, is it should end up being the difference of the two energies. Hopefully this kind of makes sense if you're used to the operator notation. If you don't, feel free to let me know. Now we're actually going to make it a little bit messier, because right now I have a trial wave function. And this wave function, in all likelihood, is going to be big and messy. And as I said, it's probably not an eigenfunction of the Hamiltonian. And as you've noticed, if I'm working with things that aren't an eigenfunction of what I care about, it really sucks. So let's try and turn this trial wave function to being a linear combination, so just a sum of a whole bunch of smaller wave functions that are the eigenfunction of the Hamiltonian. And to make it a little easier, we're going to kind of go back to that to chapter 8 and chapter 7, and let's not just make it an eigenfunction. Let's make it an eigenfunction that also forms an orthonormal set. So I'm going to turn my trial wave function to a linear combination of eigenfunctions of the Hamiltonian that form an orthonormal set. Honestly, there probably exists some combination out there somewhere. Do I know what it looks like? Not so much. Do I need to? Not so much. Gotta love proofs. All we have to say is that it does exist. I don't need to know it. And of course, each of these eigenfunctions are going to occur with some probability of Cn squared. So the first eigenfunction will occur with a probability of C1 squared, the second one of C2, and so on and so forth. Now, this is where our equation gets a little bit messier, because I'm going to, now instead of having it expressing the difference in energies in terms of some wave function that I generated, I'm going to express it in terms of these smaller wave functions, which I'm going to refer to as a basis set. So this is just a set of wave functions that I'm going to use as the basis for all my calculations. Thus, the phrase comes up. It's also very frequently used in linear algebra. So in case you're familiar with some of those notations, that's where we borrowed the language from this time instead of the physicist. But when I substitute this in, it turns out that I might have a certain value of n for this wave function, a certain value of n for this wave function. So I'm going to mark them as the conjugate set is going to have values of n1, the second set of values of n2. Now this one gets a little bit messy because now I'm doing an integral of the product of two different sums. So we've done systems like this that are similar but much smaller, where it was usually two sums and two sums. So two functions and two functions. We've just amped this up to a much bigger problem. So what I did is I took a integral that I'm not sure I knew how to solve, and I turned it up to a whole bunch of simple integrals that are going to be very solvable, but there's a whole bunch of them. So this process is often easy, but very long and very tedious. But what we can then do is take this form of the function, and as you may have noticed, it's very long, so I'm going to want a way to simplify it. So easiest approach I can do is try and bring the sums outside of the integral. And I can do this by pulling out my coefficients as well, because these coefficients are constants, so I can pull them out of the integral just fine. And when I do this, I'm now going to, instead of doing two single sums, I'm going to be doing a double sum of n1 and n2. Coefficients now on the outside, integral on the inside. Again, I'm also going to be summing over these two different possible combinations of the basis set. So again, a lot of very tedious math here. But one of the things that we can do to simplify this a lot is we established that my basis set was an eigenfunction of my Hamiltonian. Well, if that's the case, I apply my Hamiltonian, so I apply my operator to my eigenfunction, and when you apply an operator to an eigenfunction, you get the eigenvalue right on out. So this ends up becoming really nice because I now no longer have an arbitrary operator. I just have two values. This means that the difference of these energies is just going to be a constant. And if it's a constant, it means I can pull it right on out. So I took a much longer form, and now what I have is a sum of a series of constants, values I can probably just look up, and now one very small integral. And this integral is actually going to be surprisingly easy to solve because in addition to establishing that my basis set was were eigenfunctions of the Hamiltonian, I also established the fact that they form an orthonormal set, which means that the integral over all space forms Kronecker delta. So because they're an orthonormal set, they will be equal to 1 if n1 and n2 are the same. So we're going to turn those n1 and n2s just to n. And any other combination of n's are going to give me a value of 0. So this is actually incredibly useful when I look back to this summation. Because if I have any sort of sum where n1 is not equal to n2, then the whole expression drops to 0 because this term drops to 0. So that means that all I have to do is do a sum over n, because that's going to be the only case where I have a non-zero value. I just got rid of most of my possible combinations, leaving only a much smaller set. And then what's beautiful is for that remaining set, this guy drops to 1, and all I'm left with is going to be the sum of the two coefficients times each other. And again, now they're the same coefficient, just squared. And then the difference in between the energy that came from the Hamiltonian and the energy of the true energy of the system. Now, this actually becomes the real key part, because since I've got the square of coefficients, well, because they're the square, including of complex conjugates, this means this value has to be positive. And by definition of this being the true energy, it also turns out that this difference has to be positive. And this means that my value for the difference in between the energy of my guess wave function and the true energy of the system is going to be greater than 0. So it has to be positive. This also means that the lowest value the system can possibly take is going to be when E equals E naught. That's going to be the lowest value I can get. So if I minimize my energy, it means that I hopefully got my E down to equaling E naught. And that's going to be really huge. Because when we do this, this is also going to give me a way to solve my coefficients. So this is kind of a little bit of a roundabout proof, bring back a lot of concepts we haven't played with for a while. So let's do a quick take-home messages of this guy. So first, I want to emphasize that while our proof assumes that we built a wave function out of an orthonormal set of eigenfunctions, this approach doesn't require that our eigenfunctions that our basis set actually be eigenfunctions. It's just going to make the math a whole lot simpler. But what it does require is the fact that we have the correct Hamiltonian. If I don't have the correct Hamiltonian, all I will have done was minimize the wave function for whatever universe that Hamiltonian happened to be the right one. So this is going to become a much bigger deal later. One of the other big things is that using this variational principle, we can build our wave function out of any of basis set of wave functions that we're going to find useful. So the one that we often love to make use of is the hydrogenic orbitals. So these are the ones we built up in chapter 8, because these have often very nice and smooth solutions. And they're very easy to combine, as we've been doing pretty much so far all of this chapter. Finally, what this really helps me do is it gives me an approach in which I can systematically adjust my coefficients to minimize the energy of the system. So I can keep on changing my coefficients and doing that until I get the lowest energy possible. At that point, as long as I'm using the right Hamiltonian, I found the right wave function. So this is going to be a general approach we're going to use, but more importantly, we're going to be using some of these ideas as tricks that we can use to find the correct energy of the system. So we'll start playing around with that idea and doing a little bit more with determining the energies of molecular orbitals next time. Till then, take care, stay healthy.